Imagine a sweltering July afternoon. It is 104 degrees, the humidity is near maximum capacity, and the power grid goes down. In that moment, a modern home stops protecting its inhabitants and starts baking them. We build our houses as tightly sealed containers, designed to fight the climate rather than adapt to it. Keeping these sealed structures livable demands massive amounts of energy. Right now, running mechanical air conditioners consumes roughly 20% of all residential electricity in the United States. We have engineered an expensive dependency on centralized infrastructure. When the power grid fails, these structures quickly become dangerous. Yet long before the invention of electricity, ancient civilizations built thriving cities in some of the most punishing desert climates on Earth. They survived without mechanical compressors by mastering architectural physics. Look at this structure in Yazd, Iran. These clay brick wind catchers were designed millennia ago to capture prevailing breezes, funneling them directly into the living spaces. This diagram breaks down the physics they used. Passive cooling relies on three distinct physical mechanisms working together: heat control to block solar energy, heat reduction to cool the surrounding environment, and heat removal to vent. Wrapped air. When applied correctly, these three pillars can drop indoor temperatures by up to 15 degrees Fahrenheit and cut modern cooling bills by 40%. The process starts with heat control. The goal is to intercept solar radiation at the building's perimeter before it can penetrate the envelope. This cross-section shows standard double-paned glass. When sunlight hits a typical window, 76% of that solar energy passes through, converting directly into heat. But install an exterior shutter outside the glass, and you physically block that radiation. The heat bounces off, neutralizing the transfer. The roof requires the same defense. A conventional dark asphalt roof absorbs massive amounts of radiation. Applying a high albedo or highly reflective coating bounces that solar energy back into the sky, keeping the attic close to ambient air temperatures. The Stanford Hillside Passive Home in Connecticut executes this perfectly. They reject the high summer sun using perfectly angled exterior sunshades and wrap the structure, and super-insulated walls stop thermal energy at the boundary. If you fail to stop the heat at the exterior, the structure becomes a greenhouse. Once thermal energy breaches the walls, keeping the interior cool becomes a massive energy drain. Next is heat reduction. This step focuses on manipulating the microclimate, the immediate ring of air and soil surrounding your walls. Look closely at this process. As a leaf releases water vapor, that phase change pulls latent heat from the environment, dropping the localized temperature. Biologists call this evapotranspiration. A single mature shade tree, acting as a biological heat sink, can offset the equivalent of hundreds of kilowatt-hours of mechanical air conditioning every year. Look at this underground channel. Ancient architects achieved a similar cooling effect by digging qanats, subterranean water networks that pre-cooled the incoming air before it drifted into the homes above. A house sitting on bare dirt or dark pavement will bake the surroundings. Landscape is an active, functional component of the home's cooling system. Even with perfect control and reduction, humans and appliances generate heat indoors. The third pillar, heat removal, focuses on flushing that accumulated energy into natural environmental sinks. To manage this, builders use thermal mass materials. Exposed concrete, stone, or adobe acts like a thermal battery. They slowly absorb the room's heat throughout the peak hours of the day, stabilizing the indoor air temperature. But a battery has to be emptied. We do this through night flushing, by opening the house. When the sun goes down, that stored heat is purged out of the heavy materials and into the cooler night air. To drive this air exchange efficiently, architects rely on natural stack ventilation. A modern application of this is the MCC building in New Zealand. In this 3D model, cool air enters the ground floor, gathers heat, and rises. The central atrium creates a pressure gradient, pulling warm air out the top. The same aerodynamic principles powered ancient solar chimneys and Arabian wind towers. This vertical pathway cycles air continuously, turning a stagnant trap into a self-regulating respiratory system.
Passive design is an interconnected ecosystem. You cannot treat these three pillars as a checklist where you only pick one or two. A common retrofitting mistake is stuffing a house with heavy insulation and airtight seals to keep the cold air in while completely ignoring the need for fresh airflow. Without a mechanism for heat removal, the insulation traps ambient moisture and human heat. The walls sweat, creating an environment perfectly calibrated to breed toxic mold and rot the framing. Implementing one strategy while ignoring the others puts the house at war with its own physics. When the components don't work together, the entire system fails. But when you align control, reduction, and removal, the results speak for themselves. You get a silent, draft-free home with continuously filtered air and drastically lower monthly utility bills. In Masdar City, these modern metal lattices execute the same aerodynamic physics developed by ancient Persian engineers. These towers regulate the temperature of the entire plaza without a single mechanical compressor. Reliable, long-term energy independence is built directly into the geometry of a house that works in partnership with the physics of its environment.
In the average American household, keeping the interior cool accounts for roughly 20%. True energy independence relies on redesigning your structure to naturally reject heat rather than paying for more power to fight it. Step 1 is heat control. Your first line of defense is the building envelope. This requires bringing your attic up to modern code and recoating your roof with a white liquid elastomeric paint to reflect solar radiation. Please also include a radiant barrier, as shown here. A reflective aluminum foil must be stapled specifically to the underside of the attic rafters to bounce radiant heat away before it can reach the ceiling. This creates a common failure point, the moisture trap. You must never lay this foil flat on top of your floor insulation, as it will trap moisture and accumulate dust, rendering the barrier useless. Securing the roof and attic provides the most cost-effective way to prevent the bulk of the sun's radiation from pushing down into your living space. Windows are the next critical vulnerability. Accounting for up to 30% of residential cooling energy loss, the difference between these two methods is vital. On the left, an exterior awning stops solar radiation before it touches the glass. On the right, interior blinds allow heat to pierce the glass first, where it becomes trapped inside the room. For windows that cannot be shaded externally, applying a low emissivity, low-E solar film to the glass provides a secondary shield against solar gain. This sequence prevents the oven effect. If you insulate your attic but ignore the windows, you inadvertently turn your home into a greenhouse that permanently traps heat inside. Step 2 is heat reduction. Now we move to the yard to create a pre-chiller for the air surrounding your home. This top-down view shows the optimal placement for deciduous shade trees. Planting on the east, west, and northwest exposures successfully blocks the harshest low-angle sun throughout the day. These trees cool the area through evapotranspiration, releasing water vapor to absorb latent heat. You can amplify this effect by replacing dark asphalt near the house with light pavers or dense ground cover to eliminate radiated ground heat. In dry climates, integrating a water feature or courtyard pond directly adjacent to your living space uses evaporation to naturally cool the ambient temperature. Down-engineering a cooler microclimate reduces the initial heat load that your house has to fight against. The final pillar is heat removal. Because some heat will always penetrate your defenses, you need an effective way to move it out. This requires thermal mass. These traditional adobe structures utilize thick, heavy earthen walls to stabilize interior temperatures. In a modern home, you can achieve this by exposing concrete slabs, stone or tile floors in rooms that receive afternoon sun. These heavy materials act as a thermal battery, slowly absorbing afternoon heat to keep indoor air stable and cool. To empty that thermal battery, you need stack and cross ventilation. As hot air rises, it must be allowed to escape through vents or windows at the highest point of the house. Without proper ventilation and thermal mass, a house cannot exhale.
Your previous heat-blocking efforts will eventually fail as the structure becomes saturated with heat. The essential daily routine that activates this entire system is known as night flushing. The parameters are simple. Seal the house tight during the day, then open the windows wide at night. This diagram shows the process in action. Once outdoor temperatures drop at least 5 degrees below indoor levels, cool air sweeps in to flush the stored heat out through the roof. Note that in highly humid regions like Houston or Miami, heavy night flushing is less effective because it can import unmanageable moisture into the building. By applying control, reduction, and removal, the home becomes a self-regulating machine. This results in total quiet and a 40% reduction in cooling bills. Implementing these structural upgrades establishes the foundational first step toward true long-term energy independence.